Earth's path around the sun. This will be a short lesson looking at the fact that Earth travels around the sun, and because of that we can see different stars at different times of the year. We'll also be considering several other ideas as well. First, a couple of big ideas. One, the Earth spins on an axis. You probably knew this. The axis is an imaginary line that goes through the north and south poles and extends into space in both directions. And you've probably seen pictures like this before. Shows the Earth, a line coming out of the North Pole, that orange line there, and one coming out of the South Pole. Arrows on here indicating the direction that the Earth turns on its axis. Another idea, you've probably heard this before. As the Earth orbits the Sun, the rotational axis of Earth is always parallel to the same direction. We'll make a little animation of that here. I've got a reference Earth that's just sitting still up there, and something that you can see if you look carefully here is that the axis of the traveling Earth is remaining parallel to that of the stationary Earth. The axis keeps the same orientation all the way around. Turns out there's a very slow change in that axis orientation that we'll look at in a few days, but over the course of a human lifetime you would never notice it. So, some more big ideas. The scale of things. We'll have many changing scales in astronomy, and distances are surprisingly large sometimes. But in the classroom, I have a scale model of the Earth, Sun, Moon system, and there's a yellow ball hanging in the back of the room, styrofoam ball that is about the size of a tennis ball, I think, and that represents the Sun. And then I have the Earth-Moon system drawn on an 8.5 by 11-inch piece of paper. The Earth is a tiny dot on that piece of paper. It's about the size of a period on a typed page, that is. And the Moon's orbit is a small circle drawn on there. And the Moon's orbit is only about 2/3 the size of the Sun, and so pretty small. Now, how far apart should I put those things? Well, I had to back up a ways to be able to get the orientation correctly. Here's the classroom. It's kind of a mess right now. I haven't cleaned it up. In fact, I can't even go there supposedly most days, but sometimes I sneak in to take pictures. Okay, up in the stuck to the ceiling is that Earth-Moon system paper. Most people never even notice it in the classroom, but it's up there. And then in the back of the room is that tennis ball sized sun. And in between the sun and the Earth, we'd have a couple of planets, Mercury and Venus, but other than that, it's pretty much empty space. There's a couple other styrofoam balls hanging from the ceiling in there as well, but they're a different model, so ignore them for the time being. So we have a scale model with the sun as a small yellow ball and the Earth is a tiny dot on a piece of paper. About 2/3 of the way across the classroom. That's roughly, it's a little over 20 feet. And the Moon's orbit around the Earth is a little smaller than the small yellow ball. Where is the next nearest star? You may have heard the name of it. It's called Proxima Centauri. And on this scale model, the nearest star, a red dwarf star, would be about as big as a golf ball. It's not as big as the sun, it's a dwarf star. And how far away do you think it would be? I've had people guess before. They'll say downtown Moses Lake, or Ephrata, Kennewick, Pasco, someplace down that direction, maybe Seattle. would be as far away as El Paso, Texas, and that is the nearest star to us. Nearly all the stars that you see in the night sky are many, many times farther away than that. And so that's pretty amazing. We've got a pretty big universe. Now, if the nearest star is as far away as El Paso, Texas, it doesn't matter where you are standing on Earth's orbit in relation to that yellow ball, you're going to be looking the same direction to see something in El Paso, Texas. So, as the Earth orbits the Sun, our location changes by an insignificant amount compared to the distance to even the closest stars. And when we look in the direction of a particular star, we're always looking in the same direction in space, no matter where we happen to be in our orbit around the Sun. And the size of our orbit is just too small to have much of an effect compared to those huge distances to stars. Okay, a little bit of an activity we would do if this were an on-ground class here. I made some charts years ago, and I did it because students often had the idea that if you couldn't see a certain star some time of the year, that the reason was that it never got above our horizon that time of year. And I'm going to try to disavow you of that notion. But, these charts have a black dot in the center of them that represents the sun. Of course, that sun is too large for the scale of things that we're going to have, but that's okay. And then there's a circle surrounding that black dot that represents the Earth's orbit around the sun. And when we're doing this in class, I give you some little markers that represent the Earth that have kind of a clock built onto them. And I can have you have some little people standing on the Earth as well if you want. But anyway, we'll just do it a little more simply here. On the outer edge of these charts that I have, first thing you might notice are a bunch of dates on there: August 16th, 18th, 21st, 24th, 26th. Every 2 or 3 days on this, I made a mark. Took a while to get all these things in here. And something else you might notice is Leo. That's a constellation that's in the night sky. It's a nice springtime constellation. And then there are a couple of other markings. But the dates that are around here correspond to when the sun would appear against those background stars, that particular part of the sky. So in late August, actually from about August 11th until September 17th, the sun would appear against the background stars of Leo. A couple of other things that are on here that we won't be making use of yet, but there are hour markings here, and there's something called the celestial coordinate system, and it uses 2 coordinates, one of which is analogous to latitude on the Earth and another is analogous to longitude, and these hour markings are like the lines of longitude on the Earth's surface. So we'll learn about those later in the quarter. Okay, back to our big chart here. We're going to have an arrow point directly through the sun to a point in the sky, and the date that it'll hit will be August 26th. And so from an Earth viewpoint, the sun would appear in that part of the sky on August 26th in Leo. The stars in that part of the sky will not be visible, not because they're not above the horizon, but because they're up at the same time as the sun. And the sun is pretty darn bright. The only time you could see these is if you happen to be looking toward this part of the sky during a solar eclipse, a total solar eclipse. And in fact, on August 21st, 2017, I was down in Oregon in the path of totality of the eclipse that happened that August, and I could see one of the bright stars of Leo during that eclipse. I have a picture of it that I'll show you when we talk about eclipses, probably next week. On August 26th, right inside that little circle there, the little red circle, is where the Earth would be in its orbit around the Sun. August 26th, that's where the Earth is. We'll keep that spot circled. Here's where the Earth would be on October 15th. And now a line drawn from that point where the Earth is through the Sun hits in the constellation of Virgo on the October 15th date that I've got up there in Virgo. So during that stretch of time, from August 26th till October 15th, the Earth moves to the right counterclockwise in its orbit around the Sun. And so it's changed position, and because of that, the Sun appears against a different backdrop of stars. Now, while that was going on, the Sun appears to move to the left against the background stars from the Earth's viewpoint. But of course, it isn't the Sun that's moving. It's the Earth that's moving. It's because of our change in position that the Sun appeared to change position. Okay, this time I've picked a different date to have the line through the Sun hit, and I used a new color of line. I was getting tired of red. This is the location of the Earth on September 4th. A little bit different than where it was on August 26th, but still in pretty much the same part of its path around the Sun. And up there at the top, you can see the stars that would be overhead at noon on September 4th. Okay. When you look in that direction at noon, you'll be looking at the Sun, and just about straight overhead, or at least if you were on the Earth's equator, they would be, you'd see those stars of Leo up there. At the bottom of the chart, we have a new idea here. That's where the stars that are overhead at midnight on September 4th will be. At midnight, you're on the opposite side of the Earth from the Sun. Okay, at noon, you're on the side of the Earth facing the Sun. At midnight, you're on the side of the Earth facing away from the Sun. And the stars that are overhead are down there at the bottom of the chart. That's in the constellation of Aquarius. And I can vouch for that. Early September, you can see the stars of Aquarius in the nighttime sky. Meanwhile, about 6 months later, on March 2nd, that's where the Earth is going to be. It's traveled halfway around the Sun since September 4th. And so now it's up there. Now, at noon on March 2nd, you'll be looking from the new location of the Earth through the Sun, and the stars that would be overhead, which you can't see because it's daytime, would be the stars of Aquarius. At midnight on March 2nd, you'd be facing away from the Sun on the Earth, and the stars that would be overhead would be those of Leo. And so you see a different batch of stars. We could do this month by month all the way around the year and see what stars are behind the Sun and not visible to you at that time, and then what stars are overhead at midnight. So we've got some ideas that we can tie together here. As we orbit the Sun, as the Earth orbits the Sun appears to move against the background stars. It also makes them impossible to see. And even though those background stars are not visible while the Sun is in that direction, they are still above our horizon every day. In 6 months' time, the stars which are high overhead at noon will have shifted to where they are high overhead at midnight. And that's because the Earth has moved to the opposite side of the sun. And finally, any particular star or constellation will be above the horizon the same number of hours every day of the year. But if those hours happen while the sun is also up, we can't see them. So those are a few basic ideas about things that happen. And these are discussed somewhat in chapter 1, in those first few sections of chapter 1. They may not go about this quite the same way, but the ideas are in there to some extent.